Hi guys! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about highway and railroad engineering. At ang magiging topic natin in today's discussion guys is all about reverse curvature. At sa discussion natin ngayon, we will be discussing the definitions of a reverse curvature, the different types of a reverse curvature, and at the later part of this discussion, I will present three different problems that will show you how reverse curvatures can be solved. So, puntahan natin guys itong definition ng reverse curvature. Pag sinabi nating reverse curvature, this is composed of two or more simple curves that are turning in the opposite directions and with their common tangents at their junctions. So kapag daw ang curves natin ay turning in the different direction, unlike in the compound curvature where they are turning in the same directions, then we have what we call a reverse curvature. And in the reverse curvature, their centers, the centers of the curves are located in the opposite sides of the common tangent. Very common, ang reverse curvature ay ginagamit natin when we are laying things such as pipelines o kaya ay flumes na kung saan ang requirement for super elevation is not an issue. However, there are still engineers that are using reverse curvature. However, they are used on a low speed roads and railroads. Kasi nga magkakaroon tayo ng problema as to the requirements of the super elevation if we will be using a reverse curvature without any transition. Kaya ito ay ginagamit lamang sa mga low-speed roads and railroads. So, ng mga halimbawa ng sinasabi nating reverse curvature, I have here some illustrations of a reverse curvature where you can find how they are connected. So, in the illustration, we have here a reverse curvature where this part of the curvature from here up to this part hanggang dito actually is a reverse curvature. Diba? Na kung saan the curves are turning in the different directions. So we also have here an example of a reverse curvature. So we have here a series of reverse curvature from this point, mula dito sa side nito, okay, side nito, hanggang dito, and then hanggang dito. So we have here a series of simple curvatures that are turning in the different directions. So you have here reverse curvature. We also have here a reverse curvature that are applied in railroads. However, in railroads there are some requirements. So mapapansin niyo somewhere here, itong part na ito nakita natin is a transition. So meron tayong tinatawag transition that would allow the transition of one direction into the another direction. And so you have here what we call a reverse curvature. So, in the study of reverse curvature, kailangan nating intindihin or alamin ano ba itong mga tinatawag nating types of reverse curvature. Pag sinabi nating types, we have here at least 4 different types. The first is called a reverse curvature having parallel tangents and equal radii. Kapag meron doon tayong tangents that are parallel and the radius of the curvatures are equal, then we are having the first type of the reverse curvature. An example of this type is that whenever you have here parallel tangents and on the parallel tangents, we connected a reverse curvature that runs in this direction. Kumbaga, from the center of this common tangent, we draw a line that is perpendicular, and then at the same distance from the point of intersection up to this point, we connect, we call this as our V sub 1. And from V sub 1, we draw a line and we try to measure a distance equal to the tangent distance also. And from here, we draw perpendicular line so that you have here what we call the center of the first curvature. So we have here the center of the first curve. And on the other side, from here up to the point, we call this as the second vertex of the reverse curvature. And so, to determine the other point on the reverse curvature, we measure, nagme-measure tayo ng distance equal to this point from V sub 2 towards the common tangent, one of the common tangents. So, we measure this distance, So at the end of that distance, we draw a line that is perpendicular so that we are able to locate the center of the second curvature. Okay, this element will have, okay, this as the curvature that runs in that direction. Okay, and then you have here the straight line. This reverse curvature would have the following elements, such that you have here our back tangent, our PC, our point of the reverse curvature where we can find our common tangent. So you have here also the PT and the forward tangent. So this reverse curvature, meron tayong tinatawag na radius, okay, which are equal in magnitude, ano? And so you also have here the eye of the first curvature also being equal to the eye of the second curvature. And so you have here the reverse curvature having a parallel tangents of an equal radii. Take note that here the radius of the curvatures are equal, so that, okay, the central angle of the two simple curvatures of the reverse curvature are also equal. Yung pangalawang tinutukoy nating type ng reverse curvature ay yung tinatawag na reverse curvature having parallel tangents but unequal radii. Kapag itong ating PRC dito, itong ating PRC or the point of reverse curvature is moved from the center of the common tangent either closer to V sub 1 or closer to V sub 2, anong nangyayari dyan? Nababago na ngayon ang kanilang radius, but their eyes will remain the same. And so when you have that kind of changes, then we will have a reverse curvature having parallel tangents and unequal radii. So ipakita natin halimbawa na kunwari, ito yung ating mga element, galawin natin to point of the reverse curvature. Either we move closer to V sub 1 or V sub 2. But I will be moving it to V sub 1. Kapag ginalaw natin itong ating PRC, definitely we have to also move our PC so that this distance from here up to that distance will also be the same as the distance from here up to that distance. Di ba? Ganon din dito, kung itong ating PRC will be moved further from V sub 2, we have to move also a P sub T further from a V sub 2. Kaya ang mangyayari, we will have a radius that are different, but we will still have the same central angle of the simple curvature of the reverse curve. Okay, pakita natin. Okay, tingnan natin itong mangyayari. Okay, so nakita niyo ano? Balikan ko lang para makita natin yung animation. Yan, balik ko lang ha. Yun, ganyan yung mangyayari, oh. So that our reverse curvature will run from the back tangent towards the PC, papunta doon sa PRC, and then from PRC, papunta sa PT, and then from PT, papunta dito sa forward tangent. And that becomes our reverse curvature having parallel tangents and unequal radii. So tandaan natin dito, ang ating radius are not equal, but our central angle of the reverse curvature remains the same. Yung pangatlo nating type ay yung tinatawag na reverse curve having converging tangent and equal radii. Ibig sabihin nun, itong dalawang tangents na ito, yung back and forward tangent, if they will be meeting or intersecting, then we call this as converging tangent. Ba? So if we will have this forward tangent intersect the back tangent, then we shall be having tangents that are converging. And what will happen is that we shall have here a reverse curvature having converging tangent. And if it happens that our radius of curvature are equal, then they have a equal radii. Therefore, this is what will happen when we have, pakita natin mabuti, ganyan yung mangyayari. Okay, tingnan nyo, no? So, pakita ko ulit mabuti. Okay, so let us show the animation. When you have here, when the two tangents converge, okay, we shall have here a converging tangent. So, ano ngayon mangyayari sa ating curvature? So, from the back tangent, okay, okay, mag-end siya sa PC, then from PC towards PRC, then from PRC towards PT, and then from PT towards the forward tangent. That becomes now our reverse curvature. So, in this case, we have R1 equal to R2, and our I1 is not equal to I2 because we have a converging tangent. And the fourth one is when you have a reverse curvature having converging tangent and an equal radii. So again, if we shall be moving this PRC either closer to V sub 1 or V sub 2, what will happen is that the R1 will not become equal to R sub 2. Somehow, okay, we may find that R1 will be larger than R2 or R2 larger than R sub 1. And let us find what will happen when we try to move the PRC para makita natin. So if we'll be moving PRC, dapat kailangan na yung ating PC at yung ating PT will also be moving so that their distances from PRC to V sub 2 will be the same as the distance from V sub 2 to the PT. Ganon din from PRC to V sub 1 will have the same distance as V sub 1 to PC. Kaya pag ginalaw natin yan, ito yung mangyayari. Tingnan natin mabuti Okay? So I move it closer to V sub 2. So ano ngayon nangyari? Yung aking R sub 1 ay medyo humaba. Okay, humaba. At umikli yung ating R sub 2. Kaya yung ating reverse curvature will run in this direction from the back tangent towards the PC, then from PC towards the PRC, towards the PT, and then from the PT patungo dun sa ating forward tangent. So, and then in this case, ang ating R sub 1 is not anymore equal to R sub 2. And also, our I sub 1 is also not equal to our I sub 2. Ngayon ay puntahan naman natin itong different elements of reverse curvature. So we have the following. The first, we have the point of curvature. When we say point of curvature, it refers to the point where the back tangent intersects the first simple curvature, or it is the beginning of the reverse curvature. In our illustration, our PC will be represented by that point. The point where the back tangent intersects the reverse curvature. The second element is what we call the PT, or the point of tangency. And when we say point of tangency, it is the point where the curve ends, where the curve meets the forward tangent. And in our illustration, this is our PT. Okay. The next point or element is called as the PRC, also called as the point of the reverse curvature. The point of the reverse curvature is the point where the first curvature meets or joins the second curvature. The intersection between the two simple curvatures of the reverse curvature. And in our illustration, this one shall be our point of the reverse curvature. So that is our point of the reverse curvature. Yun. Okay? So the next element is we have here the tangent distance of the first curve. The tangent distance of the first curve is the distance from the point of intersection of the back and the common tangent to the point of the curvature. And in our illustration, this is our T sub 1 representing this also distance. The next point is our T sub 2, also called as the length of the tangent of the second curvature. It is therefore the distance from the point of intersection of the common tangent and the forward tangent known as V sub 2 to the point of the reverse curvature or to the point of tangency. So that this length is called as the length of the second tangent, or the length of the tangent of the second curvature, also called as this distance. Okay. Next element is you have the vertex of the first curve. The vertex of the first curve is also known as the point of intersection of the back tangent and the common tangent. And this is normally called as V sub 1. In our case, it is our vertex of the first curve. The next element is called as the vertex of the second curve. It is actually defined as the point of intersection of the common tangent and that of the forward tangent. And here is our V sub 2. Next element is the central angle of the first curve. Okay, the central angle of the first curve is the angle subtended by the curvature of the first curve known as this element. Okay, and we also know that this element is also equal to this angle, the deflection angle between the back tangent and the common tangent of the simple curvature, and that is also this angle. The next element is the central angle of the second curvature, which is called as this angle. Okay, so this angle, our central angle of the second curvature. Next element is the length of the first curve. The length of the first curve refers to how long is our curvature from PC to PRC, and represented here by the blinking arc or curvature. The next element is the length of the second curve. The length of the second curve is the arc length from PRC to PT of the second simple curvature of the reverse curvature. This is the blinking arc of the second curve. The other elements of the reverse curvature are the following. So let us show here the length of the first chord. The length of the first chord refers to the distance from the PC to the PRC. So this is what we call the length of the first chord, and we are normally denoting it with L sub 1. The other element is the length of the second chord. The length of the second chord refers to the distance from the PRC to the PT, and that is our L sub 2. And lastly, we have here the length of the common tangent, referring to the distance between the point of intersection of the tangents of the first curve to the point of intersection of the tangent of the second curve. And this is this tangent, the one that is blinking in blue. Okay, so let us now try to show an example of how we are to deal with problems in reverse curvature. And as I have mentioned a while ago, I have prepared 3 problems to show how problems about reverse curvature can be solved. And so let us have this our sample problem number 1. It says here that the perpendicular distance between 2 parallel tangents is equal to 8 meters. These tangents are connected by a reverse curvature such that the central angle is 8 degrees, and the radius of the curvature of the first is equal to 175 meters. Find the radius of the second curve of the reverse curve. So in order for us to be able to solve the problem, okay, maybe we could it could help us if we shall be able to draw the illustration. So what we do is to analyze the problem one by one, and as we analyze the problem, we draw the reverse curvature from the given elements of the curve in the problem. So let us start with the situation that the curvature here says that the perpendicular distance between the parallel tangent is equal to 8 meters, meaning we have here this parallel tangent whose distance is 8 meters. Then the tangents are connected by a reverse curvature such that the central angle is 8 degrees. So how are we going to show it? So let us try to connect these parallel tangents by a common tangent that is running from this point up to this point on the curve. And assuming that somewhere here, somewhere between these 2 points, we consider our PRC. And then from the PRC, we try to draw a line that is perpendicular in order for us to determine how the curve will run. And from this point, measuring a distance equal from the first vertex equal to a distance, so that at this point we shall be drawing a line perpendicular, so that you shall be having here the center of our first curvature. And on the other side, we measure a distance equal to this length towards the direction of the forward tangent, so that somewhere here we shall be having our PT, and then drawing perpendicular line so that we can have here our location of the center of the second curvature. And the curvature will have a central angle equal to 8 degrees, which is also equal to this 8 degrees. And if you are going to show the elements of the curvature, okay, that 8 degrees will also be the same as this one. So you have here our curve that will run from the PC towards the PRC towards the PT. So that, okay, if we're given the radius of the curvature that is equal to 175, this radius will represent this, okay, distance, the length of this line joining this point up to this point, as well as this point up to that point, and you have here 175. And so from here, we are required to find for the distance, the magnitude of the second radius of the curvature. So in order for us to be able to draw or to solve this problem, so let us try to imagine, okay, defining the elements so that we have here our PC, our PRC, and our PT. Let us call this as our B sub 1, and this will be our B sub 2. And if we are to draw, okay, a line that is passing through the PRC, which is parallel to the tangent line, let us imagine that, okay, through the PRC, we draw a line parallel to the tangent line, so that we shall be drawing this line, okay, drawing that line. And assuming that this point shall be called as A, while this point shall be called as B. Okay, so when we draw line parallel to the tangent lines, we have divided the parallel lines into two, okay, separate, so two magnitudes, such that this distance may be called as X, while the bottom one may be called as Y. Now, if we're going to consider, okay, we're going to consider triangle A, PRC, and O sub 1. Actually, we are referring to this triangle A, PRC, and O sub 1, this triangle. So you would notice that from this triangle, we can find the relation between A and O sub 1 and that distance of PRC to O sub 1. So that, okay, the ratio of the side of A to O sub 1 to PRC to O sub 1 is equal to the cosine of the angle theta, so that A to O sub 1 can be found, can be computed as R sub 1 cosine of 8 degrees. But because we are given R sub 1, which is equal to 175 degrees, 75 meters, therefore we can solve for A O sub 1, which is equal to 175 cosine of 8 degrees. And so from here, we can solve that A O sub 1, which is this distance from this point up to that point, shall be equal to 173.297 meters. However, we're going to look at this illustration. This distance X will also be equal to this distance. As such, we can find the value of X because X and the distance A to O sub 1 is also equal to the radius of the curvature, which is equal to 175. And so from here, we can solve for the value of X because R sub 1 is equal to A O sub 1 plus the value of X. So that X will be equal to 175, representing our R sub 1, minus 173.297, hence X will be equal to 1.703 meters. Now, after we have solved for this X, you can find that X and Y, okay, the sum of X and Y will be equal to 8. Therefore, we can solve for the value of Y as the difference between 8 and X. So that here, we can solve that Y is equal to 8 minus X, which is 1.703. So that Y can be computed to be 6.297 meters. This Y is equal to 6.297 meters. What is the purpose of showing and computing for the value of Y? Because you can find that from the triangle BPRCO, so this triangle BPRCO, I am referring to this triangle. Okay, so that let us imagine this triangle be colored so that we can find this triangle, okay, clearly. We can identify, and we can find from this triangle the ratio that B sub O to B to O sub 2 to the ratio of R sub 2 is equal to cosine of central angle A. So that from here we can find that B sub O2 is equal to R sub 2 times cosine of a 8 degrees. So that from here we can solve for r sub 2, so that r sub 2 becomes BO sub 2 times cosine of 8 degrees. But what is BO sub 2? If we're going to look at the illustration again, BO sub 2 is the difference between r and y. Diba? R and y. So you can find that, okay, BO sub 2 is equal to the difference between R sub 2 minus y. And from here, if we will be substituting y to be equal to 6.297 and r, okay, in this relationship, so that we can substitute that r sub 2 will be equal to r sub 2 minus 6.297 divided by cosine of 8 degrees. And so you have here a simple formula equation involving r sub 2. So from here we can solve for r sub 2 to be equal to 647.05 meters. And that is how we can solve. Okay, we have shown an example of how we will be dealing with problems on reverse curvature having parallel tangents. Okay, and I hope that you are able to follow. For us to be able to further strengthen or understand the concept, let us try to study the second problem. The second problem goes like this. The two underground roadways AB and CD are to be connected by a reverse curvature of common radii with tangent points B and C. If the bearing of the line AB is south 83 degrees 15 minutes east, line CD is south 74 degrees 30 minutes east, and that of the line BC having a length of 350 meters is south 56 degrees 35 minutes east, find the following. We are required to find for the length of the common radii, and letter B, find for the stationing of the PC, PRC, and PT if point B representing the stationing of the point of intersection of the first curvature is at station 5 plus 100. Okay, so again, it would be better to analyze and to consider drawing the reverse curvature out of the given element as mentioned in this problem. So one by one, try to analyze the given, and from the given, let us try to draw our reverse curvature. Let us try to imagine the first given. There is a given direction of the first tangent AB, which is at south 83 degrees 15 minutes east. So if we're going to show that direction, let us try to imagine that somewhere here is our point A. So that from A, we try to draw our direction, and so we try to indicate where is AB be directed, considering that it is directed from south 83 degrees 15 minutes east, therefore it will be directed in this direction, somewhere in this direction. And let us try to find this direction by drawing this line having the magnitude of the direction equal to south 83 degrees 15 minutes east. At the end of that line, we shall be calling this as our point B. The next given in the problem is our BC. BC has a length of 350 meters and directed at the direction south 56 degrees 35 minutes east. So from B, we try to identify where is C be located. So let us try to find the location of point C by looking at how it is directed. We have here south 56 degrees 35 minutes. So somewhere here we shall be locating our point C. Let us try to locate that point. This is our 56 degrees 35 minutes east. This point therefore is our point C, and has a distance of 350 meters. So let us try to indicate the distance of 350. Now, the next distance or the next element is the line CD. The line CD has a direction of south 74 degrees 30 minutes east. So from point C, try to establish the location of point D by establishing the line CD with the direction indicated at 74 degrees 30 minutes is. So from here, we try to indicate where is that 74 degrees 30 is somewhere here. We will locate it in this direction. Okay, so here is our point D therefore, and we will be calling it as our line D. So this becomes now our direction of the tangents indicated in problem. So what do we do next? So let us try to find the different elements. So we are to find for the length of the common radius. So if we will be establishing somewhere between B and C, our point of the reverse curvature, and assuming that it will be somewhere here, somewhere here. And then we try to draw a line that is perpendicular to BE in order for us to be able to understand where will be the location of the centroid or centers of the okay, curvatures of the reverse curvature. We try to draw this line which is perpendicular to BE. And then from point A, we try to draw a line perpendicular to AB so that we shall be able to locate this position, this being the center of the first curvature. Similarly, we try to draw a line perpendicular to CD, that is passing through D in order for us to be able to locate the center of the second curve. And so we have here our center of the second curve. And so we expect therefore that our curve will run from the common tangent, from the back tangent, towards A, and from A it will start to curve, running from A towards this point known as the PRC, that direction. And then from here, it will be running in this direction towards the curvature in the opposite direction. Then from D, it will be running along straight tangent. And so you have here the direction of the common, reverse curvature. Okay. So how do we define the other elements? So let us try to consider that this is our radius of the curvature, having also the same distance as this radius. Take note that in the problem, we are given that there are common radii, meaning the radius of the curvature are equal. So assuming that this point, we have here our R sub 1 being equal to R sub 2, and we expect that I sub 1 will not be equal to I sub 2. We expect that I sub 1 will not be equal to I sub 2. Now, let us imagine that point A will be our PC. Then, this point shall be called as our PRC, and the point D will be our PT. It is mentioned in the problem that point B, as indicated here, is at station 5 plus 100. This point B representing B sub 1, or the point of intersection of the first tangent. That B is at station 5 plus 100. If this is at this station, we will be looking for the stationing of A representing the PC, the stationing of this point representing the PRC, and the stationing of the D representing the PT. We are also required to find for the magnitude of the radius of the curvature R sub 1 and R sub 2, these two being equal. Okay, so let us try to find out, let us try to solve the problem by solving first for I sub 1, or the central angle of the first curvature. The first curvature has the central angle, which is also the same as this angle. As you would notice, it is also equal to the deflection angle of the common tangent from the back tangent. And if you are going to analyze this value, this I sub 1 will be equal to the difference in the direction between the direction of the back tangent and the direction of the common tangent, representing 83 degrees 15 minutes and 56 degrees 35 minutes. So that I sub 1 therefore will be equal to 83 degrees 15 minutes minus 56 degrees 35 minutes, so that I sub 1 will be equal to 26 degrees 40 minutes, or in terms of decimal, it will be equal to 26.67 degrees. Similarly, we can solve for I sub 2, and we will find that I sub 2 will be this angle, also representing the deflection angle of the forward tangent from the back tangent. Ipakita ko ito dito that this will be our I sub 2. Itong angle na ito mula dito hanggang dyan. And this can be computed as the difference between the direction of okay, the back forward tangent and the direction of the back tangent. So that I sub 2 will be equal to a 74.74 degrees 30 minutes representing the direction of this forward tangent minus 56 degrees 35 minutes representing the direction of the common tangent. That is actually our value. And so I sub 2 will be equal to 17 degrees 55 minutes. So after we have solved for, okay, the I1 and I2, now let us try to, okay, go back to the given in the problem. It is mentioned in the problem that the distance from B to C is 350 meters. And we will find that that distance B to C is also called as the common tangent of the reverse curvature. And so from that observation, we can say that the common tangent of the reverse curvature being equal to t is equal to the sum of t sub 1 plus t sub 2. But we understand in our discussion with the simple curvature that t sub 1 is equal to r sub 1 times tangent of I sub 1 over 2. Similarly, we can find for t sub 2 as equal to the product of r sub 2 times tangent of I sub 2 over 2. But if r sub 1 is equal to r sub 2 and t is equal to 350, therefore we can substitute all of these values. Okay, the value of t sub 1 expressed in terms of r sub 1 and r sub 2 as well as that of t in the formula that t will be equal to r sub 1 times tangent of I sub 1 over 2 plus r sub 2 times tangent of I sub 2 over 2. So that if we will be substituting the value I have here, 350 representing this given value will be equal to r sub r times tangent of the first angle that is equal to 26 degrees 40 minutes over 2 plus r k representing k the common radius multiplied by the tangent of the second k second central angle that is equal to 17 degrees 55 minutes is equal to this magnitude divided by 2. And so if we have here an equation involving r, so we're going to use our calculator. We can solve for r to be equal to what? 886 0.88 meters, the value of the common radius. Now, after we have solved for the value of the common radius, we will be solving for the stationing of A or the stationing of the PC, as well as the stationing of the PRC and the stationing of D, which is also defined here as our point of tangency. And how are we going to solve for the stationing of PC? We will find that stationing of PC will be equal to the stationing of P, okay, having a magnitude of 5 plus 100 minus this value representing t sub 1. And so we can solve for that stationing by solving for t sub 1 first. So stationing of the PC therefore will be stationing at B minus t sub 1, where the value of t sub 1 as we have known will be equal to r sub 1 times tangent of I sub 1 over 2. We have just computed r sub 1, which is equal to 800 80 something, so when we substitute that value, we shall have here 886.88 times tangent of 26 degrees 40 minutes divided by 2. So we can find that the value of the first tangent will be equal to 210.19 meters. Now after we have solved for this t sub 1 representing this magnitude, so we can solve for PC, stationing of the PC, by subtracting this value from the stationing of B, so that our stationing of the PC will be stationing 5 plus 100 minus t sub 1, and therefore our stationing of the PC will be 4 plus 889.81. That's how we solve for stationing of the PC. The next is to solve for the stationing of the PRC. And how are we going to solve for this stationing? The stationing of the PRC will be the stationing of the PC plus the length of this curvature. Okay, if the length of the curvature will be computed using chord basis, therefore this will be equal to stationing of the PRC will be equal to stationing of the PC plus LC sub 1, where our LC sub 1 using the chord basis computation of the length of the curvature will be equal to 20 times I sub 1 over D. Okay, where the value of D can be computed using its relation with the R, and that is equal to 1145.916 over R. Now substituting the value of the radius of 886.88, so we can find for the degree of the curvature to be 1.303356 degrees. Now after computing for this degree, well, now we can substitute it in this formula so that we can solve for LC sub 1 representing the length of the first curvature, so that the length of the first curvature will be equal to 20. This I, which is equal to 26.40, 26 degrees 40 minutes, may be written as 26.67 because 40 over 60 is 0.67 divided by the degree of 1.303356. We can find for the value of the length of the first curve to be 318.13 meters. Now after we have solved for this value, we can compute for the stationing of the PRC, so that stationing of the PRC will be 4 plus 489.81 representing the stationing of the PC. By adding the length of the first curvature of 317.13, we shall be getting stationing of the PRC to be at 5 plus 206.94. Now finally we can solve for the stationing of the PT, where stationing of the PT can be solved using stationing of the PRC and the length of the second curvature. Na kung saan our length of the second curvature, again, using the chord basis, we shall have 20 times I sub 2 over 2. We are given I sub 2. Okay, we already have computed I sub 2, and we have computed also D sub 2, which is equal to D sub 1 because R1 is equal to R2. Therefore, we can substitute the value where our R sub 2 will also be equal to 1.303356. And that if this will be substituted here, we can find for the length of the second curve to be 20 times 17.92 divided by 1.303356 gives us a value of the length equal to 274.93. And then finally, we can solve for the stationing of the PT to be equal to the stationing of the PLC plus the length of the second curvature, so that stationing of the PT will be 5 plus 206.94 plus 274.93 representing this length equal to stationing of the PT to be 5 plus 481.87. And that gives us the complete solution to the second problem when you are dealing with a reverse curvature that have a converging tangent, but in this kind of example, we have the radius of curvature being. The third problem that I have prepared is a more interesting problem because we have here a problem that will deal with the fourth case of fourth type of the reverse curvature having converging tangent and radius that are not equal. And so let us try to work on this problem. Let us try to consider this problem. A reverse curvature connects two converging tangents intersecting at an angle of 30 degrees. The distance of this intersection from PI of the second curve is 150. The deflection angle of the common tangent from the back tangent is 20 degrees, and the azimuth of the common tangent is 320 degrees. The degree of the curve of the second curvature, or simple curvature, is 6 degrees, and the stationing of the point of the intersection of the first curve is 4 plus 450. So we will be determining here stationing of the PC, the PRC, and the PT. Again, it will be interesting to solve for the problem, and it will help us solve the problem fast if we shall be able to draw illustration. And so let us try to draw the illustration, the reverse curvature, out of the given elements from the problem. Let's start with the given problem. There are, according to the problem, converging tangent intersecting at an angle of 30 degrees. So let us try to imagine that we have here tangents that are intersecting at an angle of 30 degrees. This angle of intersection at point B is 30 degrees. But the next given is that in the problem we have here the deflection angle of the common tangent from the back is 20 degrees. If we will be calling it as our back tangent, then from here, there is a common tangent whose deflection angle, whose angle measuring from the common tangent is 20 degrees. And assuming that this angle will be our common tangent, that angle will be making this angle to be 20 degrees. What else is given? Okay, we are also given that the distance of the point of intersection of the second curve from point B. Okay, from point B. The distance of this point is 1. From point B is given to be 150 meters as indicated in the problem. What else is given? So that the degree, the azimuth of the common tangent, this distance or this azimuth, this common tangent has an azimuth of 320 degrees. Okay, this azimuth is 320. Tamang-tama yung ating illustration. That is about 320 degrees. We are also given that the stationing of the point of intersection of the first curve is at 4 plus 450. Knowing that this will be our common tangent making an angle of 20 degrees with the back tangent, therefore this position will become our point of intersection of the two tangents of the first curvature. That is actually the intersection of the back tangent as well as the common tangent, and therefore this becomes our B sub 1, but having the stationing at 4 plus 450. Okay, from here, therefore, we shall be solving for the stationing of the PC, and the PT. We try to locate where is our PC, and the PT. Now let us try to locate our PC. Imagine that our PC is somewhere here. That will be our PC. Then our PRC will be somewhere located between B sub 1 and B sub 2, and whose distance will be the same as the distance of B sub 1 to PC somewhere here. This will be our PRC. So that we are going to draw our PRC, our PT will be located along this line, and whose distance will be equal to the distance of this distance from here up to that point. So somewhere here will be our PT. Ayun. Diba? And in order for us to draw our curvature, let us try to draw our curvature by drawing a line perpendicular to our PC. So here's our line. Similarly, we draw line perpendicular to the line B1, B2 passing through PRC. And so we have this line so that we shall be able to locate our center somewhere beyond our illustration, our canvas. Okay, and from the PT, we draw a line perpendicular to the line V sub 2 to V, so that we shall be able to locate our center. So, okay, so here is our radius of the first curvature, and this will be our radius of the second curvature. Okay, so in order for us to determine our element, let us define that this will be our I sub 1. This will be our which is equal to this one. This will be our I sub 2, and I sub 2 will be equal also to this angle. Diba? Okay. So let us now try to define that I sub 2 and I sub 2, which is actually an unknown quantity here. Now let us try to imagine that our curve will run from our back tangent, will end at PC. Then from PC, it will have a simple curvature towards PRC. Then from PRC, another simple curvature in reverse direction toward PT. And then from PT, towards the forward tangent. And so you have here our reverse curvature. And so, in order for us to solve for the problem, let us now try to solve for the value of I, considering the triangle V sub 1, V sub 2, and V. Here's our V sub 1. Here's our V sub 2, and that is our B. Let us try to imagine this triangle. Define this triangle. I will color it 1, and let us try to transfer this triangle here for evaluation purposes. Our B sub 1 is here. Here is our B sub 2, and this is our B. This distance 150 is equal to this magnitude. You have 20 here, therefore this is also equal to 20. This angle is 30, therefore you have 30 here, and this angle will be equal to I, which is I sub 2, which is equal to this angle I sub 2. This angle being supplement to I sub 2, therefore this angle will be equal to 180 minus I sub 2. And knowing that the sum of the interior angles of a triangle must be equal to 180 degrees, then we can solve for I sub 2 by adding all of these triangles being equal to 180 degrees. So that, okay, 20 plus 30 plus the quantity 180 minus I sub 2 shall be equal to 100. And you will find that these two 180s will cancel each other, and we can find for I sub 2 to be equal to 50 degrees. Then after we have solved for 50 degrees, we can compute for T sub 2. This T sub 2. And how are we going to compute for T sub 2? Because in the problem, we are given the degree of the curve of the second curve. And if we are given the degree of the curve of the second curve, we can compute for its R. And because we have just computed for I sub 2, we can compute for this T sub 2. Knowing that the formula for T sub 2 is equal to T sub 2 equal to R sub 2 times tangent I sub 2 over 2. Where we have already just have computed for I sub 2, that is equal to 50. We just need to compute for R sub 2 given that D sub 2 is equal to 6 degrees. Therefore, we compute for our R sub 2 equal to 1145.916 over 6 gives us a value of D sub 2 of R to be equal to 190.986. And if these values are substituted here, we can compute for our T sub 2. Our T sub 2 therefore will be equal to 190.986 times tangent of 50 over 2. This gives us a value equal to 98.058. Now after we have computed for this T sub 2, what shall we do? We can compute for the length of the common tangent using the sine law. Where is our common tangent? Our common tangent is actually the distance between V sub 1 to V sub 2, where this can be found in our triangle here representing this distance from that point to this point. And because we already have known all of this sides, but we can apply a sine law so that the ratio of V sub K1 to V sub 2 is to sine of 30, the opposite side, opposite angle, is equal to 150 is to sine of the opposite angle of 20. So from here we can compute for V sub 1, V sub 2 to be at 243.6568 meters. And that is our length of the common curve. But because the length of the common curve is equal to the sum of T sub 1 and T sub 2, therefore from here we can compute for T sub 1, where T sub 1 will be equal to this distance, the distance of the common tangent minus T sub 2, that is equal to the common tangent minus T sub 2. Substituting the common tangent to be at 243.6568 and the tangent distance 2 of 89.058, we can compute for T sub 1 to be at 243.6568 meters. I'm sorry, minus 89. That gives us a value equal to 154.5986 meters. After solving for T sub 1, we can now compute for the stationing of the PC, because the stationing of the PC is equal to stationing of B sub 1 minus the tangent distance T sub 1. Therefore, we can compute next for the stationing of the PC, that the stationing of the PC is equal to the stationing of the vertex minus T sub 1, where the stationing of the vertex sub 1 is given at 4 plus 450. We just have computed 154 for T sub 1. We simply substitute it here, so we can compute for stationing of the PC. That is 4 plus 450 minus T sub 1 equal to 154.6, giving us the stationing of the PC to be 4 plus 295.4. So that actually gives this stationing. Now, if we wanted to compute for the stationing of the PLC, then from PC, we simply added the length of this curvature. So that solving for the radius of the curvature R sub 1, how do we solve for the radius? R sub 1 will be T sub 1 over tangent of I sub 1 over 2. We just have computed T sub 1 and I sub 1. So we can compute for R sub 1 to be 154.6. From here, divided by tangent of 10. That gives us a value of r sub 1 equal to 876.77. So from r sub 1, we can compute for d sub 1. Ba? And that d sub 1 is equal to 1145.916 of r sub 1, giving us a value of equal to a 1.301 a degrees. After we have computed for this degree, we can compute for the length of the first curve. By a chord basis, it will be equal to 20 times I1 over d sub 1, where I1 is equal to 20. So substituting the value here, 20 multiplied by 20 divided by 1.301, giving us a value of 306 or 307.46 meters. Now, knowing this value, we can compute now for the PRC, because stationing of the PRC will be equal to stationing of the PC plus the length of the first curve. That if this will be substituted, we shall have here a value of 4 plus 295.4 plus this length of 307.46, giving us a value of the PRC, which is equal to 4 plus 602.686. Okay, that is the stationing of the PRC. And then finally, we can compute for the stationing of the PT by adding the length of the second curve, so that the length of the second curve can be computed again by the k-chord basis, that is equal to 20 I sub 2 over d sub 2. That this will be equal to 20 multiplied by 50, and the degree of the curvature being given of 6. So we can compute for the length of the curvature of the second curve to be at 166.67. And then finally, adding this to the stationing of the PRC, we can compute for stationing of the PT. So that stationing of the PT will be equal to stationing of the PRC plus the length of the second curvature. That gives us a value of 4 plus 602, this one, 0.86 plus 166.67, giving us the final value for the stationing of the PT to be at 4 plus 769.52. And so guys, that's how we present our example on the reverse curvature. And I hope that with the presentation that I have given you, you're able to understand what is a reverse curvature, what are the different types of reverse curvature, the elements of the reverse curvature, and how are we going to solve problems that will deal with reverse curvature. Once again, thank you very much for watching.